If you know just how acidic a solution is, it can offer a lot of useful information. Even in your aquarium, if it gets too acidic, your goldfish are going to die, right? Even inside your own body, as your blood gets more and more acidic, worse and worse things keep happening. You could be brewing beer, and you're monitoring pH the entire time. The pH in it, or the acidity in a bioreactors. Again, very important. Otherwise, your little bugs aren't going to do their job. What we use to monitor pH is a pH scale. And in this convention, neutral solutions have a pH of 7. And acidic solutions have a pH less than 7. And basic solutions have a pH greater than 7. So acidic solutions are like stomach acid, lemon juice. Basic solutions, ammonia, soda. Your human blood is somewhat basic. Self-ionization, it's also called auto-ionization. It's also called dissociation. These are all the same words for water falling apart, right? The self-ionization of water. Water can dissociate to hydrogen ions and hydroxide. So if we want to write an equilibrium constant expression for that, K is hydrogen ion concentration times hydroxide divided by 1, right? Because it's a liquid, so that doesn't show up. Whenever you have to write a reaction in a particular way, it's an important reaction, and they give a subscript on that equilibrium constant, so it's an important number. And that number is 1 times 10 to the negative 14 at room temperature. So this equilibrium constant is a very small number, right? This reaction hardly even gets started. It's almost all in the backwards direction. Water is a very, very weak acid, right? It doesn't produce hardly any hydrogen ions at all. So here are some helpful hints to predict the pH of strong acid and base solutions. So just know these things, and that will help us out in the homework. Know the formulas of the 6 strong acids. Well, remember the periodic table gave us half of them, HCl, HBr, and HI. Then the others were like nitric acid, perchloric acid, and sulfuric acid. Know the formulas of the strong bases. So the periodic table will give us half of those too. Lithium hydroxide, sodium hydroxide, and calcium hydroxide. Okay. The remaining 3 are really right here. Calcium, strontium, and barium hydroxides. These are +2, so we're going to have 2 hydroxides there. Calcium hydroxide, strontium hydroxide, and barium hydroxide. So there's our strong bases. Solutions of strong acids and bases always dissociate 100%, and we're going to see what that means when we start working some problems. Some equations to calculate pH. I give you these equations, we just have to know how to use them and manipulate them. There's 2 ways to find the hydrogen ion concentration, equation 1 and equation 4. So let's take a look at these. In equation 1, we have pH equals a negative log of the hydrogen ion concentration. So how would you solve that for the hydrogen ion concentration? Well, bring the negative sign over to the other side. We'll have a negative pH equals a log of the hydrogen ion concentration. Raise both sides to what power to cancel out that log, the 10. Right? And the 10 and the log cancel out, and what you're left with is 10 to the negative pH equals the hydrogen ion concentration. How about equation 4? How would you rearrange this for the hydrogen ion concentration? Well, just bring this to the bottom, right? So we'll have a hydrogen ion concentration would be 1 times 10 to the negative 14 all over the concentration of hydroxide. So there's two ways to find the hydrogen ion concentration. Likewise, there's two ways to find the hydroxide concentration. Equations 2 and 4. Here's equation 2. POH is the negative log of the hydroxide concentration. Bring the negative sign to the other side. We'll have a negative POH equals the log of hydroxide. Raise both sides to the 10 power. 10 to the negative POH equals the concentration of hydroxide. Right, because 10 and log are inverse functions. And you could also rearrange equation 4. Right, for hydroxide. So that would just be hydroxide would be 1 times 10 to the negative 14 divided by the hydrogen ion concentration. So there's our two ways to get hydroxide. Okay, let's play with this a little bit. If the hydrogen ion concentration is 3.8 times 10 to the negative 3, what is pH? Well, the equation we should pick is pH, the negative log of the hydrogen ion concentration. That'd be the easiest way. So, the negative log of 3.8 times 10 to the negative 3. Let's see what we get. So put in 3.8 times 10 to the negative 3 first. Log, and minus it, about 2.42. If the pH is 2.85, what's the hydrogen ion concentration? So again, it would be easiest to use this equation. Okay, but we need to solve for the hydrogen ion concentration. So we're going to have 2.85 equals the negative log of the hydrogen ion concentration. Bring the minus sign over, and then we'll raise both sides to the 10 power. Right, raise both sides to the 10 power. So then the 10 and the log cancel out. Okay, so we have 10 to the negative 2.85 is our hydrogen ion concentration. So what does that equal? So 10 to the, I'm just using the x to the y button, 2.85, make that negative. I get about 1.41 times 10 to the negative 3. Yeah, how about if the pH is 8.35, what is the hydroxide concentration? So there's a number of ways to solve this. Okay, I think the easiest way would be to use this one. Let me show you why. pH plus POH is 14. pH is 8.35. So my POH has to be 14 minus 8.35, about 5.65. Now I can use my other expression. POH is the negative log of the hydroxide concentration, right? So 10 to the negative POH will be my hydroxide concentration. So 10 to the negative 5.65 will be hydroxide. So 5.65, make it negative. 10 to that power, shift 10 to the x. 2.24 times 10 to the negative 6. Okay, let's try this one. What is the hydrogen ion concentration in 0.25 molar HCl? Strong acid, so that means 100% dissociation. And that's how all these homework problems are going to be for today. So that means the hydrogen ion concentration is 0.25 molar. It breaks up 100%. The chloride concentration is 0.25 molar, but we don't care about that. What is the hydroxide concentration in 0.15 molar NaOH? Again, strong base. So that means 100% ionization, 100% dissociates. So the concentration of hydroxide and sodium too, they're both 0.15 molar. What is the hydrogen ion concentration in 0.15 molar NaOH? Well, in 0.15 molar NaOH, we know that the hydroxide is 0.15 molar. So we can use our expression, Kw, which is 1 times 10 to the negative 14, is hydrogen ion times hydroxide. So 1 times 10 to the negative 14 will be hydrogen ion times 0.15 molar. So my hydrogen ion concentration will be 1 times 10 to the negative 14 divided by 0.15, about 6.67 times 10 to the negative 14 molar. What is the pH of 0.05 molar NaOH? Well, I think it'd be easier to do this. Let's find POH first, right? This has to be, concentration of hydroxide has to be 0.05 molar. So POH right, which is the negative log of hydroxide, would be the negative log of 0.05. 0.05 log, about 1.3 is my POH. Subtract that from 14 and I'll have pH, right? Because pH plus POH is 14. So my pH will be 14 minus POH, which would be about 12.7. So 12.7 would be my pH. What are the concentrations of hydronium ion? Remember, don't let that confuse you. It's the same as H+. And hydroxide in each of the following. 1.2 molar HBr. Well, that means that the hydronium ion concentration is 1.2 molar. And that concentration of hydroxide would just be Kw divided by that hydrogen ion concentration. So 1 times 10 to the negative 14 divided by 1.2. 1 times 10 to the 14 negative divided by 1.2, about 8.3 times 10 to the negative 15. A detergent has a pH of 11.63. What is the hydroxide ion concentration? Okay, a couple ways to solve this. I think the easiest is to, if you know pH, it's easy to find pOH. Right, because the sum has to be 14. So 14 minus 11.63 is about 2.37. So there's my pOH. And remember, 10 to the negative pOH is the hydroxide concentration. So 2.37, make it negative, shift 10 to the x, 4.27 times 10 to the negative 3. Which of the following pH values indicate an acidic solution? Well, if it's less than 7, acidic. Which are basic, which are neutral? Well, that will be neutral. That's 7. Acidic again, less than 7. Greater than 7, basic. How about obtain the pH corresponding to the following hydronium ion concentrations? Well, this is the concentration of hydronium ion. But remember, that's just the same as hydrogen ion. And since pH is the negative log of hydrogen ion concentration, all you have to do is just take the negative log of it. So 7.5 times 10 to the negative 3 log and negative 2.12. You take the negative log of 7.5 times 10 to the negative 3, you got it. Obtain the pH corresponding to the following hydroxide concentration. Okay, so this is the concentration of hydroxide. So I say let's find the pOH and subtract that from 14. So pOH is the negative log of hydroxide. So that's going to be the negative log of 5.25 times 10 to the negative 9. 5.25 times 10 to the negative 9 log, about 8.28 is my pOH. So my pH would be 14 minus pOH. Around 5.72 will be my pH. Okay, now these questions are going to be getting a little more complicated. If 2.8 grams of NaOH is added to 250 mils of water, what will be the pH of the solution? Okay, so let's use this information to get the concentration of hydroxide. And then we'll use one of our pH expressions, equations, to get pH out of this. So if we have 2.8 grams of sodium hydroxide, 250 mils of water, what's the concentration of hydroxide? Our concentration units are molar, and that's always moles over liters. Well, the liters part is 250 mils. That's going to be 0.25 liters. The moles, always have to calculate it. We have 2.8 grams of NaOH. Let's just convert it into moles. Whenever we're given moles, we can convert to grams. What's the molar mass of sodium hydroxide? Sodium is 23 plus oxygen 16 plus 1 for hydrogen, about 40. So I have 40 grams in a mole of NaOH. So around 0.07 moles of NaOH. If I have 0.07 moles of NaOH, how many moles of OH do I have? The same number. Do you see it? In 1 mole of NaOH, I have 1 mole of hydroxide. Right? 'Cause look at the chemical formula. It's 1 to 1. It's the same number. So my concentration of hydroxide then is going to be 0.07 moles all over 0.25 liters. About 0.28 molar. Okay, if that's the concentration of hydroxide, my POH, just take the negative log of it, it's about 0.553. So then my pH, right, subtract from 14, well, 13.45. If 250 mils of 0.29 molar HCl is added to 250 mils of 0.55 molar HCl, what will be the pH of the final solution? Okay, what we need to do is find that hydrogen ion concentration, right? And the hydrogen ion concentration, the concentration really of anything, is its moles divided by the liters. Okay, let's find the liters first. That'll be the easy one, I think, because the liters is just the total volume. And what's our total volume in liters? It'll be this volume and this volume. So it'll be 0.25 liters plus 0.25 liters. So we've got the volume. Now let's find the moles. To find the moles, we'll find the moles. Let's clean this up a little bit. Find the moles of H plus here. Find the moles of H plus here and add them up, and we'll have it. So we'll have 0.25 liters times 0.29 moles per liter plus 0.25 liters times 0.55 moles per liter. So my total moles is going to be what? 0.25 times 0.29 plus 0.25 times 0.55. Well, 0.21. Okay, so now I can finally get my hydrogen ion concentration. My hydrogen ion concentration is going to be, like we said, moles over liters. So that's going to be 0.21 moles of hydrogen ion divided by 0.5 liters. 0.42 molar hydrogen ion. Is that what they wanted? No, they wanted pH. So let's take the negative log of it. .38. That will be my final answer. If 50 mils of 0.9 molar HCl is added to 25 mils of 0.5 molar HNO3, what will be the pH of the final solution? Notice that this question is really the same thing as what we just did. It doesn't matter that these acids are different. They're both strong acids. So we do the exact same thing. We find that the concentration of hydrogen ion is going to be the total moles of the hydrogen ion divided by the total liters. So do the exact same thing, okay? My total volume will be 0.075 liters. How about my total hydrogen ion concentration? Let's see if we can figure that one out. So add up those moles. I'll have 0.05 liters times 0.9 moles of hydrogen ion in a liter plus 0.025 liters times 0.5 moles in a liter. See, my liters cancel. .05 times 0.9 plus 0.025 times 0.5, about 0.0575 moles of hydrogen ion. So I can get my final answer here. My hydrogen ion concentration will be the moles, 0.0575 moles of hydrogen ion divided by that total volume, 0.075 liters. .77 molar. So my pH, take the negative log of that, about 0.115. Last one. If 8 grams of calcium hydroxide is added to 3,000 mils of water, what will be the pH of the solution? We're given hydroxide, and we're given the grams, so we can get moles of hydroxide out of this. And here's our volume. So if we combine these two, we can get the concentration of the hydroxide. Moles of hydroxide all over the volume. And then from there we can get our pH. So let's see how we can get this to work. Our volume is just 3 liters. How about our moles of hydroxide? That's going to be a little more work. Our moles of hydroxide, let's find. Okay, we have 8 grams of calcium hydroxide. So you see the game plan here? Let's convert this into moles of calcium hydroxide, and then we'll convert that into moles of hydroxide. So just one long step here. Let's find the molar mass of calcium hydroxide. Calcium is 40.1 plus oxygen, 2 of them, 32, plus 2 hydrogens, you get about 74.1. 74.1 grams in a mole of calcium hydroxide. Okay, if I have 1 mole of calcium hydroxide, how many moles of hydroxide do I have? And the answer is in that chemical formula, right? If I have 1 of these, I have 2 hydroxides. And stop there because you want moles of hydroxide. So everything on top multiply, bottom divide. 8 divided by 74.1 times 2, about 0.216. So that number we're going to put up top. Okay. So that 0.216 over 3, about 0.072, 0.072 molar hydroxide. Okay, let's take the log of it. We'll have POH, subtract it from 14, and we'll have pH. Log of that is 1.14. Is my POH. Subtract that from 14, and I'll have pH, 12.9 about. Okay, so 12.9 will be the pH of 8 grams of calcium hydroxide when placed in 3,000 mils of water. So the idea here is to know how to use these equations in combination with knowing these strong acids and these strong bases. And then just realize that in some of those more difficult ones, hydrogen ion concentration will be the total moles of hydrogen ion divided by the total volume. Or if you're after hydroxide, the total moles of hydroxide divided by the total volume.